Hello, everyone. Good morning. I am Debanjan Konar. I am currently working as a postdoctoral researcher at Center for Advanced System Understanding, Helmholtz Laboratory in Germany, and I have done my PhD from IIT Delhi in the last year, 2021. Okay, so before I start, let me just tell you that that this work is my PhD work, and we are developing quantum-inspired self-supervised neural network architectures. And one of the work that is Qutrit-inspired fully self-supervised shallow quantum learning network for image segmentation, and this work is published in IEEE Transaction on Neural Networks and Learning Systems. So before I start going to the actual presentation, let me just tell you why we need the quantum-inspired or Qutrit-inspired or qubit-inspired computing in our novel self-supervised neural network architectures, because you know that the classical self-supervised neural network architectures suffers from convergence problems. So we have made a novel attempt to introduce quantum-inspired computing into our self-supervised neural network architectures to make it a faster convergence. So these are the items in our presentation, that is the introduction, motivation and contribution, basic concepts in quantum computing. And then we will discuss about the basic quantum neural network model based on qubits. So that is D level quantum bits, or in generic level, it is D levels. And for 3 levels, it's called Qutrit. So Qutrit inspired fully self-supervised shallow quantum learning network model that we have developed in our research. Then we will see how we can segment the images, grayscale images using our network, that is QFSNet. Then we'll also talk about some of the results and conclusion and references. Okay, so all of you have heard the term the quantum computing supremacy, and everybody is saying that it can be achieved through superposition of quantum states and quantum entanglement properties. However, it is an uphill task due to lack of quantum hardware available in current scenario. So right now, the classical system embedded with the quantum formalism of quantum-inspired computing are become popular, and in addition, there are some hybrid classical quantum algorithms are becoming also popular. So these algorithms, whether it's hybrid classical quantum or quantum-inspired neural networks or quantum-inspired algorithms, these are not able to exploit the full advantage of quantum superposition and quantum entanglement. Hence, it is quite difficult to bring some quantum entanglement and quantum advantage in classical simulations. So here we have made an attempt to make it qubit instead of qubits in algorithm or qubit in qubits neural networks, where we can have some marginal advantage over qubits. So in the past, there are various quantum-inspired neural networks, as though it's written as quantum ANN, but indeed it is a quantum-inspired network because it is no quantum hardware implementation is done. But right now we are also working on some of the quantum neural network which are already implemented on quantum and hardware using VQC, variational quantum circuit. So in these quantum ANN models, so you can see that these are the very promising quantum algorithms, and it can be implemented on noisy intermediate scale quantum devices. Okay. And these networks are successfully applied in various applications like image classification, pattern recognitions. So some of the work is already cited here, including ours. However, as I told you that this network is already implemented on classical platforms without taking care of any variational quantum circuit or quantum hardware. And another problem is here we apply quantum backpropagation algorithm, that is very time intensive algorithms. So that is we tried to avoid it in our neural networks. So the main motivation I have just spoke about, that the classical self-supervised neural network architectures are basically suffer from image segmentations. Okay, so we have in past also tried to propose the quantum version of classical self-supervised neural network architectures for image segmentation using qubits. However, the convergence of the network architectures are not as much which we are expecting. So because the reason behind it is that the quantum neural network or quantum inspired neural network based on qubits are based on bilevel abstraction, but in reality, most of the physical implementation of quantum systems, it is a multi-level state. So qubits, though it is, we do not dare to implement d-level information systems, so we are just sticking to 3-level, that is called Qtrit. So here, basically, whenever we approximate the lead-level system into bi-level system, we are approximating and suppressing more higher levels, and that basically leads to error. So if we can have, instead of bi-level, we can have tri-level, though it is not fulfilling the entire essence of these quantum states, but it can marginally give some improvement. So that the PVT model leads to some untimely convergence and destroyed outcome, but still it is better than some classical networks. So here we have made a D-level qubits model that can be applicable for qubits, qtrits, and so on. In addition, in our contribution, we have also developed a multi-level sigmoid activation function that is inspired by Qtrit. And here we have tried to use the quantum superposition and entanglement, although entanglement bodies is very difficult to get any advantage on classical systems. So for the validation purpose, we have validated our model on Barclay datasets, that's grayscale images, and as well as some medical images, because our network is self-supervised network architecture and it is more suitable for medical images where annotated data is limited. So this is a very basic concepts of quantum. I'll go through very quickly. So QDIT, a QDIT system is a superposition of D-level models, that is 0, 1, 2 up to D-1 at the information levels, and alpha 0. These are the alpha squared, alpha 1 squared. These are the probabilities in occurrence of 0, 1, and 2 respectively. And if you add this probability, it will give you 1. Okay, so in addition to this for Qtrit, it will be 3 levels. You can see from this equation 2 that psi is a superposition of 3 states, alpha 0, 0, 1, and 2, and where alpha 0, alpha 1, alpha 2 are the coefficients. Okay, and if you add the square of them, then it will give you 1. So in addition to Qtrit, we have also employed some of the quantum operators like poly operators. Okay, they are on qubits in general. So poly operator is mod 3 operator. It works like on modulus 3 operations. And another very important gate we have used, that is Hadamard gate. So Hadamard gate is basically used to just get the superposition of any basic states. This is a matrix representation. Here we have not implemented any quantum hardware. We have taken a help of all these matrix operations in this case, and it is more suitable for image segmentations. Okay, so this is the more generic case of Hadamard gate. Sorry, special case of Hadamard gate. And in addition to Hadamard, we have also used rotation gate. Rotation gate is used to update the interconnection weights. So this is our rotation gate, and here and j omega 3. So here the rotation angle is omega. So we have also developed a D-level quantum neural network model. Okay, so you can see the acquisition function. We have any segment acquisition function. First, we have input our classical bits to quantum bits by some amplitude encodings. So that is twice pi by d and this, and then we have it converted to some qubits. So these are all quantum inspired. It's not actual qubits. Then we have gone through some of the operations in the quantum using auto operators like cos twice pi k divided d. This is nothing but a Hadamard gate we have used, and as well as the realization operations. So realization operation is basically helps us to get the actual informations. Okay, so here you can see the real and imaginary part of the each and every qubits are basically mapped using the T gate. So these are the mathematical. I am not going into that due to limited time. So these are mathematical derivations. So this is a basic neural model where input and output, where we have given two important and arguments. One is your activation, another one is your threshold. So that's two I have set here. Okay. So now coming to our neural network, proposed neural network architecture. This neural network architecture is basically comprises 3 layers: input layer, intermediate or hidden layer, and output layer. And you can see that in each layer, each and every pixel are considered a Qutrit in this case. And classical bits is basically converted by quantum amplitude encoding scheme. And then we have applied Hadamard gate to get the superposition of the states. Then we have applied rotation gate to modify the interconnection weights between input to intermediate output, and output to intermediate. So input and intermediate layer is basically connected to forward propagating interconnections. And you can see that I have shown only one of these, that the red pixel is a candidate pixel. The considering there is a candidate pixel, it forms 8 connected neighborhood based pixels. So this is acting as like a convolution map. So here I have shown only one. So if you consider each and every pixel as a candidate pixel, always there will be 8 connected from except the corner and edge pixels. So in that case, you have to take the dummy pixel as your edge pixel. So this is the way actually 8 connected neighborhood information is basically propagated to the corresponding candidate neuron to the next layer. And this is the way the intermediate layer is also connected with the output layer. And from output layer, again, it is going back to the intermediate layer. And this process is carried out until and unless there is some error of network weights are very negligible. Now here we have used quantum counter propagation algorithm instead of quantum backpropagation algorithm, because this is fully self-supervised neural network architecture. So we do not have provision to compare the errors in terms of target outcomes. So here we have to rely on the summation of difference between the network weights between successive operations. Yes, and once this network converges, then whatever qubits are interacting with the environment, and it becomes a classical bits. So the realization of network weights. So these network weights are basically represented using cos and sine part. Okay, so this is the superimposed network weights using Hadamard gate, and we have also fixed the rotation angle as this is the difference between the candidate pixel and this neighborhood pixel, and we have taken the complement of this, that is the reason 1 minus. Then we have later on we have also encoded as a qubits by multiplying by twice pi by 3, because in Qutrit, sorry, it's Qutrit. In Qutrit, it is the enter twice pi is divided by 3. It's uniformly divided by 3 parts. That is the actually amplitude encoding phase in quantum mechanics. And here we have gone through some of the operations in using quantum operator gates, and these all are matrix operations. And this is the YLK. This is the output of a quantum neuron. And we have used Q sigma. This is not a bilevel sigma activation function. It is a multi-level sigma activation function, though I have not given that figure here. So this is the convergence of our network on various hyperparameters S1, S2, S3, S4. These are basically various cluster levels in our network architecture. Okay. And this is QISNet is basically based on qubits. That is our earlier published work, and this is our current work, that is Qutrit. So as you can see from the figure that the convergence of this Qutrit is basically much better. And here you have some hyperparameter we have used here in this case. Here we have used the number of slices as 880 number of slices in brain MR images, and you can see that the number of iterations required to complete to obtain an output or convergence of the network. So you can see that QFS net is relatively better, in more on an average. But sometimes also due to probabilistic nature of the qubits, sometimes QFS net is also taking more than classical qubits QFS net. So here we have considered very benchmarking dataset like Bartley segmentation dataset, and you can see that we have segmented using our network architecture, and we have also included in our experiment the brain MRI images from BRASS dataset as well as nature dataset. So this is the actual result on it is on Bartley dataset. So that is on human, tree, and camel aeroplanes. These are, we have reported dice similarity or dice coefficients for segmentation. So you can see that it is we are getting QFS net outperforming the others. And this is for a brain slice images, and for a slice number 37 from two datasets we have used. One dataset is your BRASS dataset, as well as another one is your from nature data repository. So these are the accuracy, dissimilarity, positive pixels, and sensitivity. As you can see that for a particular slice, it gives us a dissimilarity 0.83. You know that dissimilarity is considered the very vital in medical image segmentations. So these are the overall accuracy and dissimilarity. That is, we are 798,799. Whereas in QSNet, the qubits network, dissimilarity is 768. So we have improved the result. But still, UNet and UDesNet is much, I will not say much, is marginally higher than us. That is 806. UDesNet giving dissimilarity 806. However, despite a self-supervised network architecture, we are obtaining very good accuracies and dissimilarity compared to UNet and UDesNet, which are fully supervised. So I can draw a conclusion that an automated grayscale image segmentation using fully self-supervised network is made using Qutrit-based modeling. So here we have tried to use the intensive property of quantum states using 3-level systems, and we have obtained high accuracy and dissimilarity despite its and as a future work, we have designed a BQC, and we have also recently implemented it. Okay, so here we have used instance to 8 connected neighborhood informations. We have replaced it by BQC, and we obtained good results. This right now we are doing, and this network we have named as hybrid quantum classical neural networks, self-supervised neural networks. Okay, so this is a very simple quantum circuit. So these are the references. Thank you. If you have any question, you can ask.